All right, welcome everybody to this new ING meetup online still. I hope to see you soon in real life. Tonight we're going to do some Scala. We're going to talk about Effectful programming with Ayush Mittal, who works at ING. Some tips, a few things. We have some delay because of YouTube. So if you have questions, don't wait for us to ask. Just ask them in the chat right now so that we can easily answer. It avoids the weird blanks where the speaker has to wait for 30 seconds. So do feel free to ask questions in the comments on YouTube. One more thing, we do have our first data science meetup coming up 8th of July. So if you feel like joining, just go on the meetup page and you'll see it. No further ado, I don't think this is me that you want to hear, so I'll bring Ayush in the picture. Hi, Ayush. How you doing?
Hey, hello everybody. How
I
are
do
you?
not hear you. I hope it's everything is fine. Wait.
So, hello everybody, and welcome to the talk.
Oh, sorry for the small witness. Yeah, we can hear you, Ayush, so you can go. Just present. The floor is yours.
Okay, so yeah, no harm in welcoming again. So, welcome everybody. Welcome to this meetup for Scala. Uh, I hope this is as good as the sessions we have had previously with ING Tech meetups. And yeah, let's get started. So, a bit about me first. I'm, as Julian told, I'm working for ING and I'm based out of Leeuwarden in the north, a beautiful city. And I work for the ING team and I build contact center applications. So, when people think of contact centers, they usually think about hardwares or phone lines, but this is a fully digital contact center. We create applications that help our employees serve the customers better, the customers of the bank, and we create uh, omni-channel experience for various channels like chat, voice, video. I'm also doing some open source programming in my spare time. You can check me out in my GitHub profile at Ayush Works. That's about me. Let's set up some goals for the talk today. Uh, what are the key takeaways that we want from this talk? The topmost goal we have for this session is that we should be able to understand what are effects in Scala, and generally speaking, what are effects in functional programming. What do we mean by effects? We should be able to understand why we need effects, what are they useful for, why are they there in the language. Thirdly, we should be able to understand what side effects are and how are they different from effects, and why we should, as Scala programmer, avoid side effects. And then once we have covered effects and side effects, we should be able to understand the ideas behind libraries like cat's effects or Zio, which are quite popular in the Scala world these days. So we should achieve all these goals, but it is only possible if we make this session interactive. If you have any questions, please shoot them up front. Uh, we can always answer them. Just go ahead and ask your questions at any moment of time. So with these goals in mind, let's get started with the first topic, effects. No better way of explaining effects than by giving examples. So let's look at examples of effects in Scala. Uh, any Scala programmer must have seen the effect called option.
Ayush, I'm gonna break in just for a second. Can you try to get the mic closer from your mouth, please?
Yep. Okay. Is this better?
Sorry for that.
Yep. So Any Scala programmer must have worked with the option effect, and option basically is modeling the effect of optionality. A value might be present or it might be absent, and how do you represent that in your code? You use the option effect. So here is an example. If I want to fetch customers from my database given a customer ID, but I know the customer might be present or might be absent with that ID, so I use an option as the return type. So this notifies to my caller that, yeah, this function returns an option, and that indicates the customer could be present or absent. So this is the effect of optionality. Similarly, we have the either effect, which is the effect of one of two. So example is like, if you are trying to do some verifications or validations in your code, you generally return the either data type. There are two parts to it, left and right. The left indicates the validation has failed with an error. The right indicates, yeah, it's all good. So we'll see, we must have used as Scala programmers either also in our code bases. Another effect is list type. List is used to model the effects of 0, 1, or more than one items. So if you have conditions or if you have use cases where you need to represent scenarios where an item could be present, could be absent, or could have multiple values, then you use the list type. Example is, if I'm trying to find agents in my system that match a particular skill, I could have no agents matching that skill. I could have one or I could have more than one. How do I model this? I use a list data type. So all these data types are called as effects in Scala, and uh, these three are the pretty basic ones that we must have seen in Scala, and there are others like try, we have the reader, writer, and a host of others, but these are the pretty basic ones. The important thing about the effects in Scala is that they are popular for a reason. We'll explore the reason next. So in general, in any language, how do we build complex software? How do we go about creating a big system that is production ready, that is scalable, that is resilient? How do we do that? The trick to building any large applications is starting from bottom and going to top. So we start with small code. We start with small testable components. These small components are easy to test. They are easy to refactor. They are easy to understand by looking at them. And once we have these small components, we combine them together to form bigger applications. So this bottom-up approach is a classic 101 of how we build large, complex, resilient, reliable software applications. Now, the good thing about Scala effects that we saw, either list or option, is they compose. You can have programs that return these effects, and then you can combine these Scala effects to build larger programs. How can we combine them? These effects provide us with combinators like map or flat map. So basically we have methods on these effects, and you can use these methods to combine them to form a bigger application. We can take a small example to understand what I mean. Suppose ING is trying to build a customer marketing campaign where it is trying to reach its customers to inform them about, suppose inform them about a new scheme, or inform them about changes in the branch opening time. A customer reach campaign is what we are trying to build. To build this big application, we need two small programs. We need to call the customer, so we need the customer's phone number, and we need a method to call the actual customer. So let's look at program one. So this program basically takes a customer ID as input and returns an either, where the left indicates that the customer is probably not found with this ID, or there was some error in fetching this customer by the ID, and the right indicates the customer phone number. So this is our first basic component that we have to build this big application. The business logic is pretty simple. If we find the customer, we return the customer as a right. If we don't find it, we return an error. This is a pretty simple basic recipe to fetch the customer using his ID. The second recipe that we have is that we can, given a phone number, we can call that number. Now, again, this returns an either type because the actual connection might fail due to some reasons. Either the phone number is invalid or we could not establish the connection or whatever. So the left here indicates that and the right indicates a call. And this call, you can think of this call type as any generic type that represents a connection between you and the customer. So we have these two recipes with us, and now we want to build a final program that basically takes a customer ID and calls the customer. So how do we do that? Because generally when we compose program, the output of the first is the input to the second. But here the output is a either type and the input here is a string. So these two programs do not compose naturally, but the effect type either has combinators or has monadic operations like map and flat map, which we can use to combine them. And we will look at how we can combine them. So as I said, we have methods like map and flat map that we can use to combine or compose these. So here is how we can combine. So this is our final program or our final application where we get a customer ID and we start a call. So first we get the customer phone number using program, the first program. Upon getting that, we call the flat map method on either. The flat map method takes a number and then we can do something with that number. So we dial the customer with that number. Now the way flat map works is that if the first program, this program, if it returns an error side, then the method inside the flat map is not called at all. So we get inbuilt short circuiting, we get inbuilt error handling with this map and flat map methods. So basically two programs which were not composing naturally are now composed using the flat map method. The snippet below is the same program, but it is depicted using the for syntax. So first you get the customer phone number. Once you have the phone number, you dial the customer. If the first step fails, then the inbuilt error handling or the inbuilt short circuiting in the flat map ensures that the second method is not called at all. That is how useful Scala effects are. And that is why we like them. That is why they are so popular in Scala. So this is about effects. If you have any doubts about what effects are, we can discuss that. Please type them in the chat. Apart from effects, we must discuss another component called pure functions in Scala. A lot of discussions happen in Scala community on what is a pure functions and what is their link to effects and side effects. So before we look into side effects, let's understand pure functions in Scala. If you ask a bunch of developers what is a pure function, you might get a lot of answers. The most common one is that if your function is not having any mutable code, or if your function is not doing any mutable logic, then it's a pure function. Second answer you might get is that if a function produces same output for same input, then it's a pure function. One more variety of answer that you might hear is that if a function does not use any external variables, it's a pure function. These three are what I have generally heard from people when asked about what makes a function pure. But yeah, if you think there are others also, then please do let me know what you as a guess would say makes a function pure. These three are somewhat correct, but they do not still show the full picture. This is not a technically correct answer for a pure function. This is somewhat very near, but not the 100% picture. We can take an example and understand, and let's look at this function. We are trying to find whether a number is divisible by 2 or not. Yeah, pretty simple. Number modulus 2, if it is 0, then yeah, the number is divisible, otherwise it is not. So apart from the core business logic, there is one more line in this function which is called increment counter. Now, this function call, it looks like it is trying to increment a counter somewhere in our system. It could be a database update, it could be a Kafka update, it could be anywhere. It is trying to basically increment a counter somewhere. So if you look at this function, does this look like a pure function? If I look at the possible options that people generally guess, it does look a pure function because it does not have any mutability as we can see upfront. It does not rely on any external variable, and it always produces the same input, the same output for same input. So yeah, based on these three, we cannot say whether it's a pure function or not. Let's look at one more variant of the same program. Again, we are checking if a number is divisible by 2, but here we have a slightly funny logic that if it's a weekday, then yeah, make the check of the divisibility. But if it's a weekend, then we're not working on weekends. Throw a runtime exception saying not working on weekends. So is this function pure? If someone asks. If I look at the three hints that we generally get from people about pure functions, this also looks like a pure function because it does not do any mutability. It does not rely on any external variable. So we saw two functions that seem to be abiding by the three principles that generally people tell, but we can't say for guarantee if they're pure or not. That is because function purity is linked to a concept of referential transparency. It's not just about these three things, immutability, external variables. It's about a concept of referential transparency that we link pure functions to. So what is referential transparency? So the wiki definition is that if an expression can be replaced by its value without changing the behavior in any way, then the expression is referentially transparent. Let's divide that and understand what it means. Suppose I have an expression like this. An x is defined as 5 plus 4. Now, wherever in my code I see x, I can replace x with 5 plus 4, and the program's output will not change. So here I created a tuple of x comma x. And if I replace x variable with its value, I still get the same tuple. So yeah, this expression is referentially transparent. But this is a pretty basic insight into what a referentially transparent expressions is. What we can say is that a referential transparency guarantees purity. If your function is referentially transparent, that means you can replace the value by the expression and still get the same output, then your function is pure. There are subtle differences as to is referential transparency the very same thing as purity, because technically speaking, referential transparency is a superset of pure functions, but for our discussions, we can agree that they are the same things. So for the rest of the session, referentially transparent functions are same as pure functions. So what makes a function pure is if it is referentially transparent. And the test for a referentially transparent function is that if you replace expressions with values, you still get the same behavior. So having agreed to this definition of pure functions, why do you think as Scala programmers or functional programmers we should care about pure functions? Well, if you have spent time in applications, commercial applications, you will notice that almost 80% of the time is spent in reading code rather than writing code. You will spend a lot of time in reading the code. So reading code should be far easier than writing new code. You should be able to look at the structure of your program and understand what it does without going deep into subroutines. So if you have pure functions in your code base, reading them becomes very easy. Similarly, if you have pure functions, then instead of focusing on technicalities, you get to focus on business logic. Pure functions are easy to test. Pure functions have local reasoning to them because they are not relying on external variables. They're not uh, changing anything externally. They are locally reasonable and they are easy to understand. And refactoring with pure functions is very easy. Now, I want to especially for developers lay a extra importance on refactoring because that's what something we do a lot. And I want to give an example of how refactoring is very easy if you have pure functions to play with. Let's take an example of why refactoring is easy. So here is a function that we saw earlier, the divisibility by 2. We have the increment counter here and we have the check here. Now I'm going to prove that this is an incorrect, or this is a function that is impure, not referentially transparent, and refactoring this will not be easy. So let's see how this function is used. Let's suppose we have a software that basically takes two numbers as input and produces a boolean. And the software is basically checking if both numbers is divisible by 2 or not. There is a logical AND between the two numbers. And if both numbers are divisible, we get true, otherwise we get false. So this is how we are using this function in our software. Now comes code reviews. We go through cycles of code reviews. We have new features. So we somehow come up with code refactoring. And one refactored version of software version is like this. So what we are doing is that if both numbers are same, then we don't need to call the method for both. We can call it just for once and just return the variable from that. If the numbers are different, yeah, then we should call the divisible by 2 both times. And if you look at software 1 and software 2, it at a very high glance, it seems to be a good refactoring. It seems to be a good solution. But what someone might miss is that the divisible by 2 function was actually doing an increment counter also. It was not just checking, it was also doing an increment counter. This increment counter is something that we call as a side effect. It's something that is changing some property of the program outside. Now, software 1 and software 2 do produce the same output, but software 1 is not same as software 2. If I call software 1 with parameters 4, 4, and if I call software 2 with parameters 4, 4, I will get the same result, but the increment counter will happen only once in software 2. That means my program has changed. You might assume that you are only worried about the output of software, but when we are writing programs, we should worry about the state of the application and the entire state, not just one piece of output. Software 2 is actually doing increment counter only once, while software 1 was doing increment counter twice. So the end state, if we start using software 2, has changed, and that is very important. So that is what is the problem with writing functions like this, which have side effects or effects that basically change the outside state and are not good. So we introduce side effects now. Side effects are programs that make a program not pure. Having side effects makes our program not pure, and we do not get referential transparency with side effects. We just saw this with our example that this method, because of a side effect of increment counter, is not referentially transparent. So what are some commonly seen side effects in our code bases? A database call, update, delete, save. This is a classical side effect that we see. Logging, reading to a file, writing to a file. This is a side effect. Console, writing to console, reading to console. These are also side effects in Scala. HTTP calls. This is also a side effect. So any interaction or any code that interacts with the outside world and changes it uh, causes a change in the state of the application is a side effect. And side effects are not good because code that has side effects is not referentially transparent, is not pure, and we lose a lot of advantages if we don't have pure functions. So at this point, let's take a small intermission and just recap. Side effects we saw like database call, loggers, console operations, HTTP. These are not good for our code bases. They produce code that is not referentially transparent, and we should value referential transparency and pure functions. So side effects are bad, pure functions are good, but if you look at the list of the side effects, you will figure out very clearly that these are unavoidable. Any commercial application, any application that is worth a team that is just not a POC, any such application will have side effects for sure. So even though side effects are something that we should avoid, we cannot, because if we want to produce a meaningful software, we have to probably write to a file or make an HTTP call or have a database. We will do some interaction with the outside world and we will change the program state. So side effects are unavoidable. So this is a problem now that side effects, even though are bad, we cannot avoid them, and we are in a problem right now. And the next half of this talk is going to be focused on how do we come out of this problem. Please feel free to type your questions in the chat and we can look at them right away.
We do have one question in the chat from Ilker, who was asking if effects are specific monads. I think it's a good point because we actually reach the point where we have to mention monads. It's like it's a meetup about Scala and functional programming, so mention monads.
Yeah,
we get extra points for that. Do you have something to answer to that question? Are effects a specific monads or not?
So basically in functional domain, monads are types that allow you sequential composition. You can compose operations on monads. So any data type that provides you methods like flat map or map is a monad in Scala, technically speaking. And if you look at our effects, if you look at effects that we saw in the very beginning, option, either, and list, they all have methods like map and flat map. So yeah, they are monadic in nature and they are monads.
Is there any other question at this point of the talk?
Yeah, I think you can just continue, Ayush.
Okay. So yeah. So the stage that we are is that we have encountered side effects in our code base because we were writing code base for big companies that are production worthy softwares and not just for our small POCs. So we encountered side effects and we are in a state of bother now that side effects are not producing pure functions and we would like to have them in our code base. So what do we do? So in Scala, the trick to solving most of the problems is creating data types that help you understand the problem domain and create a solution for that. And that's what we will also do. We will create a data type that can be used to model side effects. We should have a data type that we can say represents, say, saving a file into the system, or have a data type that tells us to print to the console that side effect. So we want to create a data type that is used to model side effects. We saw effects like option or list, and they were used for various cases like option for the optionality effect. Similarly, we will also have a new effect type that can be used to model side effects. Let's understand the rules for this new effect type that we want to create to model side effects. The first important rule is our effect type is a wrapper for side effects. Basically, we take a side effecting function or a side effecting code and we wrap this side effecting code in a new type. The new type does not actually execute the side effects, it just describes them. If it executes them, then it's not worth basically creating a new type at all. This new type is only going to describe the side effect and not run the side effect. And we will see in a later slide what I actually mean by describing and not running. This new type can be used to suspend both synchronous and asynchronous code blocks, which can be affecting in nature. And most importantly, we should be able to finally run the side effect also, because we agreed that if we don't run the side effects, there's no point in actually writing the application. But the point is that running the side effect should be our wish, when and how we want to run. So these are the rules for that new data type or the new effect type that we are looking for. Now, when we think about these rules, some of you might think about futures, which is a pretty popular type in Scala for asynchronous code. And it does match some description here, like you can use future to wrap operations. So can we use futures for this? Why do we have to write a new type? Can we use futures for writing pure functions? Unfortunately, futures are not referentially transparent. And the reason for that is futures are eager in their nature. As soon as you wrap expression in a future, futures start running and it does not wait for you to tell it to run. It starts evaluating the piece of code within the future right there when you declare it. So futures are not a fit for writing pure functions or for writing referentially transparent code because of their eagerness. And a very simple example can tell you this. Let's look at this program. We have a for comprehension where we have two futures. Both the futures are doing a println of hello world. So when I run this program, I will see in my console hello world printed twice, which does make sense because there are two futures. I run them and I see hello world twice. Now, if future was referentially transparent, I should be able to inline the value. That means I should be able to take the value and replace it by the expression. That is what referential transparency was, that you could replace values by the expressions and still have the same software. So I see two values here and they are both same. This thing is same as this thing. So I'm going to create a variable and extract that. That's what I do. I create a variable future and I extract that expression in it. And then I use my variable as I was using earlier. This is program 2 is basically an inlined version of program 1. And if future was referentially transparent, program 1 and program 2 would have produced the same output, but it does not. Futures are eager in nature. This variable is evaluated only once when you declare it and is used only once. So basically the println happens only once. It does not happen twice as was the case in program 1. So inline version of program 1 is not same as program 2, and this is good enough to prove that features are not referentially transparent. Moreover, the problem with them is that as soon as you declare the future, it starts evaluating. It does not even wait for the for expression to start. Like if I remove the for expression, I will still see a println in my code. And that is because features are eager in nature. If you wrap a side effect in future, the resulting feature is itself a side effect. So you don't get any benefit basically from features. So now having agreed that feature does not fit our use case and we need a new effect type to wrap our side effects, let's design a new effect type. Let's call it f of a, where any f of a, and f is pronounced as f but is written as EFF, a fancy term. So EFF of a represents an effect that wraps side effects and produces a value of type A. And f of a is referentially transparent and separates pure and impure code. So this is a data type that we want to create in Scala to basically wrap side effects. So if you create such a data type, what requirements would your consumers have from you? The first basic requirement is a interface. You need to provide your consumers with an interface where they can provide you impure expressions like save to database, write to file, impure expressions like that. And they should be able to create an F type using the interface. That is the first requirement. The second requirement is that you need to have combinators. As we said, Scala effects like option or list are monadic in nature. They provide flat map and map. Even our new F type should provide us flat map and map method so that we can combine larger Fs from the smaller ones. And the final requirement is that we should be able to run our F type, but run at our will. And usually we'll do that at the edge of our programs, at the very end, so that the 90% of the code is pure and the remaining 10% is impure, but we only focus on 90% where we build our code. So these are three requirements from our F type that we have. So these are the simplest requirements that we have. There could be other requirements also, that you should be able to do error handling, you should support concurrency, you should support asynchrony. But for this talk and for the sake of simplicity, let's focus on a very simple F type, which is pure, which supports synchronous operations only, and which provides you sequential composition, which is basically it has monadic operations like map and flat map. So we will not consider error handling or parallelism for our F type. Let's look at the API, the first requirement, the interface that we had. So the method that we'll provide is going to be called delay. It basically takes a function or a block of code by name, and this is where you will provide a side effect. Here this parameter which is passed by name is basically telling that there will be some piece of code that will produce an A, but don't run it right now. Just take it and create a type of F. We will see how we'll create a type of this F, but this is the interface that our consumers will be exposed to. They can just provide us with any side effecting code and we will create an F type for them. The second requirement for our effect type was for combinators, that is monadic expressions to allow us to compose our F type. So we should be having methods like pure, where you give a value and you get an F type of A. The flat map, which is pretty much similar to the flat maps in other Scala effect types. You already have an F in hand. You have a function that takes the value from this F and produces another F, and that is the output of this function. This is a classic flat map, a current f of a function from a to f of b, and the output is a f of b. And you need a map where the difference is that the f is from a to b and not a from a to f of b. So these three combinators are also in our requirements for our effect type. We need these three combinators so that we can create larger programs from smaller ones. And we should provide these combinators for our new type also, for our new data type also. And we should provide a runner basically, that given an f of a, I should be able to run this f and get a value of type a. And this run is where we tell our consumers that this run method is a side effecting method. This run will produce code that is not referentially transparent and that is impure. And our consumers must be told that upfront. So this will be usually like an unsafe run or something that the consumers agree is not referentially transparent. So we have the need for the following three things: interface, a combinator, and a run method from our new data type. Do we have any questions at this point of time? If so, please feel free to type them in the chat.
Still no question, I think.
Okay. So given that we have these three requirements of a interface, of a combinator, and for runners, let's look at how we can create this in Scala. Again, we'll take small baby steps and not go into too much technical details of it. The basic idea of solving problems in Scala is using data types. Whenever you have a problem, think of a type that can solve that problem. And so we will be using a pattern called ADTs, or algebraic data types, and we will write basically case classes that represent our scenarios. So we'll have case classes that represent various situations in our code base. So we have the top trait, which is an f of a, and we have three subclasses that represent what an effect can be. We can either have a flat map situation where we have an f in hand and a function that goes from that output of that f to another f. This is one situation. The other situation is we can have a pure value in our hand, basically a value that is given to us. There's no impurity here. Or we can have a delay type in our hand. Basically, this delay type represents a function that is side effecting but not yet executed. So if you have seen option effect type in Scala, there are two subtypes, two option, sum and none. And sum represents the presence of a value and none represents option of absence of a value. Similarly, for our type f of a, we can have three possible situations where we can have an f. We can have a flat map because we have the support of combinators, or we can have a pure, or we can have a delay type. And each of these have properties like the delay type has an f which represents what is being delayed. Basically, a computation that takes nothing and produces a value of type A is being delayed. So we create a case class of type delay to represent that situation. Similarly, flat map represents a situation where we are combining our f's. Basically, we are going to combine this f with another f, and we want to represent that using a data type, and that is why we have a flat map case class. So these data types are basically going to be used to create a program using the f type. So here you can see the full picture. We have a trait f of a. This trait has two methods, flat map and map. The flat map method basically takes a function from the output of this f to another f and produces an f of b. The map method takes a function from a to b and produces an f of b. This is pretty simple. The trait f itself. We saw the data types already. We have a flat map type, we have a pure type and a delay type. So our flat map method is going to create a type of the flat map data type. You can see here that in order to create a flat map data type, we need a current effect and we need a function that goes from that output to another effect. And that is what exactly the flat map method does. So basically we are providing support for combinators, flat map and map, and we are providing support by creating data types that we designed in the previous section. So we are creating data types of flat map types in our combinator support. And finally, we have the interface, the foreign function interface, the FFI, where we have two methods, pure and delay. Somebody can say f.pure, provide a value. We will create a pure type for him. And somebody can also say f.delay. He can provide a side effecting code here, and we'll create a delay type for the user. So notice here when somebody calls a delay method, we are not going to actually run the effect or the side effect. We're just going to wrap it in a data type. And using this data type, we can further do flat map and map, and we can compose bigger applications. So now having seen the full picture, so this is a very simple effect type that we have created. We are done. We have it in with us, and now we can use this effect type and the FFI that it provides. We can use this to write pure functions. Let's create a program that is pure and is using our effect types. Let's create an echo program. Basically, you will read from console, and whatever you read, you will write it back to the console. Now, we agreed that reading or writing from consoles are basically side effects, and if we don't wrap our side effects in our effect type, the programs that we generate are not referentially transparent or they are impure. So if I don't have the f.delay here in the read from console method, then the read from console method is basically a side effecting program. But because I have wrapped the read line in the delay, I get an f of string, and this f of string represents or describes the operation of reading from console. So notice how the method read from console is actually not really reading from console. It is describing an operation that will read from console. And how have we described it? We have used our delay FFI. We have passed the side effect to this delay method, and we have got access to a type that describes the operation without actually running it. Similarly, we have the write to console method, which is println, in its root, in its naive nature, println is a side effect, but we have used again the delay method here to wrap that side effect in a effect type, and the result is a function that is referentially transparent and pure. And now we can write a program basically that is the combination of these two. That is, we first read from console and then we write to console. So we can use our flat map combinator, read from console, flat map it, whatever input you get, write to the console. So if you see these three functions, these are functions that even though describe side effects, they don't actually run them. It is just a description of how your program would behave. And this description in its nature is using these data types. It is not interacting with any outside world. It is just describing how interaction would be done. And because of this, this is a pure referentially transparent program. All the three functions here. But we have to understand what is this program is basically. This program is basically a flat map data type, because when you call flat map on any effect, you get the flat map data type as we saw here. So flat map has an effect inside it. If you see the definition of flat map, there is an effect here and a function that goes from that value of effect to another effect. So in our case, in our program, the effect is reading from the console. This is the f, that is the first parameter to flat map. The second parameter is a function that takes the value of this effect and then produces another effect. And the other effect is basically the effect of writing to the console. So you see that how we have described our program using data types. It's just a flat map of operations. Here I've also described how this program would look if you were using the for syntax and not calling flat map like it is. So you read from the console and you write to the console. So now this 90% of the code is pure, and eventually at the end or whenever we want, we can run this program. How we can run a program is, we said we will use the interpreter pattern for running our programs. Interpreter pattern means you check for data type and interpret it based on its individual type. We have three types: flat map, pure, and delay, and we'll interpret each of them separately. So here is a method that will basically run an effect. You interpret each type. So once you have an f with you, it can have three possible values. It can be a pure value, in which case you can just return the value. It can be a flat map type, which means you have an effect and a function that will run once this effect has been executed. In that case, basically you first run the first effect, pass it to the function k, you will get a effect back, and then you run the final effect again. So this is how you can interpret a flat map type. And finally, you have the delay type, where the input to the delay is a side effect that you now want to execute. So basically, you can just simply run the f. This is where side effects happen. You run them, and then you produce a type of pure, and then you run it again. So without going into too much technicalities, this is basically how you can interpret the various types and you can run them. The only drawback of this simple approach is that it's not safe to stack, because even though we have recursiveness that within run we are calling run again, it's not tail recursive. As Scala programmers, we should focus on writing recursive methods that use tail recursion, because then we are guaranteed stack safety. We can attempt a tail recursive run method also. To attempt that, always remember the flat map method. The flat map method had an f type as the first parameter and a function that goes from the output of this f to another f as the second parameter. Having this in mind, let's attempt a tail recursive version of our run. In the tail recursive method of run, we are going to do the same interpreter pattern. We are going to match against what f we have, but we are also going to keep a stack of what is left. See, if you see our program here, basically we have two steps. First, we do the read line. Once we have the read line, we do the write line. So we have basically a steps, or we have composed effects using flat map and map. So basically this second parameter represents that composition, that we have still a list of operations pending, or we have to unwind those stacks. So what we do is, when we first call the method, it's called with an empty stack, a list empty. If we come across a flat map type where the first parameter is the effect and the second is a function that goes from the effect to another effect, then we call the loop again and we add this function k to the stack. Basically we are saying that we will execute k but not right now, because we have not run the effect so far. So we have to wait to run this k function. So we add this function to the stack and we go ahead with the evaluation of our primary f type, which is in the flat map. If we encounter a delay type, that means now we are ready to execute the side effect. If this is where the bombs are fired, we execute the effect. Once we have the value ready, we call the loop method again. We wrap the effect in a pure and we continue with the same stack. If you see a pure node, that means you have two options now. Either you have come to the end of your program, that means there is no more stack left, and then basically you have the value with you. You can just return the value as it is. However, if there is something left on the stack, that means it is now time to execute it. So now if we have a pure value and there is something on the stack which is represented by this case sum, run the function on the stack using the value that we have. It will create a new type because this is a stack of that takes a value and returns a new type. So we have the new type here, the new effect type. Call the loop method again with this new type and continue with the tail of the stack. So this is a tail recursive run method, and you might be wondering what is any doing here instead of a. The point is that when you compose effects, you might do you might compose a to b and b to c and then c to again a and so on and so forth. But you will use data types like flat map, pure, and delay. So eventually, at the end of the program, you will get an a type returned. So the type safety is guaranteed because you are using the structure or the data types flat map and pure. So even though we have type any here, at the end we will be returned a type A, and the type safety is guaranteed because we have composed our programs using our data types. So we cannot go wrong in that. And it would be difficult to keep tracks of every data type, so we stick with any in the method signature. So this is how you would finally run the effect type. And if I go back to my application, the first three methods are basically referentially transparent pure functions, which are returning types of f, and f is our type of wrapping side effects. The first three functions are referentially transparent, and at the end, when we are ready with our program, we run it. This is basically saying that we are moving all the impurity to the edge of our code base. And when we run, we will read from the console first, we'll write to the console next. But when we were building our program, we were ensured that we were in control of side effects up to the point of calling run, or before calling run, we did not have any side effects in our code. So this is how you would use our F type to basically write a small program, which is 90% referentially transparent and pure. and you that is excessive or that has to scale. Then it becomes very difficult to apply local reasoning. See, we as human beings cannot look beyond more than 5-6 lines of code. We cannot keep that. Our brain stack can be not more than 5-6. I cannot remember more than 7 numbers in my mind right away. That same holds for the code also. I should be able to look at a very simple function and understand what it does without going into the technicalities of it. And if we write pure functions, we will get that local reasoning, we will get that readability, and we will be able to work with our code base better. So now we did create some effect types, but in the real world, we never have to. This f of a that we created was just an example to understand how things will work. There are lots of awesome effect libraries out in the world, and you might have heard them also. But now, hopefully, you know what they are and why you think you could have them in your code base as well. So you will never ideally need to create an effect type of your own. There are lots of them out there in Scala open source community. I am going to mention a few of them that I have worked with, or my team has also experienced with in ING. So we have Monix, which has a data type called task. We have catch effect, which has a type IO, and there are some other types also in catch effect. And the newly popular Zio library is also a library that provides you lots of effects. Which one should you use? That depends on the level of experience in your team, and also many other situations. Like if you're already using cat's core for some other purposes, then you can very well just start using cat's effect also. But whatever libraries you choose, the underlying concepts remain same. They all help you in achieving code bases that are referentially transparent, that are pure, that are easy to test, and that are basically a lot more readable, a lot more understandable than normal plain Scala code. And I think that is pretty much the end of our talk. Are there any questions?
No, we still don't have questions. Actually, thanks for your talk. I liked it a lot. I don't know much about Scala myself, but I really liked it because you basically described a lot of the Elm architecture, which is pretty much, I don't know if you know Elm, but it's front-end functional programming, and it's basically doing the same. Like you have the side effects, you can't do without it. Just put it as far as you go, as you can. And that will help you a lot as a programmer. I'm not a Scala developer. I'm guessing if you have to do HTTP calls and things like that, do you as Scala developers already work with ADTs and things like that, or like if I'm doing Elm, for example, I have to do an HTTP call. I'm just using one of the libraries that is available, and I'm ending up. It looks like I'm not doing side effects because I basically leverage the library and I end up with an ADT, and I work with it. Is it going to be the same in the Scala world?
Yes, true. So there are many HTTP client libraries that provide you ADTs that represent a REST call without doing them. So yeah, that is also true for Scala. We have some questions from the chat. I think Martin's question is already answered. Yeah.
Yeah.
Okay. Then I hope everybody has something to take away from this talk. And thank you so much for being here.
Thanks everyone for joining. See you next time.
Yeah.
And thanks Ayush for being here. I know it's not easy to talk to a computer. So
Yeah. No.
hopefully,
awesome.
hopefully next time in real life.
Yeah. See you soon. Bye bye.
Cheers, guys. Bye bye.